You assign a task to your coding agent. A few seconds later, the chat interface outputs a comforting message: database schema updated successfully. You check the actual database logs, and they are completely empty. The agent did not execute a database migration. It read your natural language prompt, accessed a file containing instructions about database schemas, and used its language prediction weights to confidently hallucinate a success state. This is a specific failure mode in agentic development, known as fake tool behavior. It occurs when a language model is forced to simulate mechanical execution using only text prediction. We arrived here because the industry rapidly shifted from stateless chat interfaces to autonomous multi-step agents. To make these agents useful, developers had to start feeding them repository structures, behavioral rules, and operational boundaries, a practice now codified as context engineering. But this produced a severe architectural ambiguity. Across the ecosystem, developers began conflating static, markdown-based instruction files with actual executable capabilities. They wrote paragraphs describing an action and expected the model to physically perform it. To build multi-agent systems that can scale securely, we have to enforce a rigid architectural boundary between semantic guidance, telling a model how to think, and mechanical execution, allowing it to act. Relying on instruction without instrumentation guarantees system failure at scale. A language model tasked with an action it cannot physically reach will always substitute text generation for actual state mutation. The base of any agentic architecture is the language model's raw context window. This is a finite computational space where every loaded rule, history log, and instruction competes for the model's limited attention. To manage this space, we establish a global semantic guidance layer, universally standardized as an agents.md file. A standard README is written to onboard human contributors. An agents.md file is strictly for the machine. It contains deterministic build steps, strict testing protocols, and baseline security constraints that the agent must respect across every interaction. However, applying a single global instruction file to a massive monorepo breaks down immediately. A front-end React package requires entirely different compilation rules and testing frameworks than a back-end Python service in the same repository. The solution is nested scoping. Instead of parsing one massive file, multiple instruction files are distributed throughout subdirectories. Agents operate on nearest file precedence. When editing a front-end file, the model reads instructions located precisely in that folder. These local rules automatically override global defaults at the root. By fetching only the contextual rules adjacent to the active working directory, the model avoids digesting irrelevant project data that belongs to other microservices. Nested scoping is the mandatory first line of defense against context saturation. It ensures the model only reads the specific rules it needs for the exact file it is editing. While agents.md provides persistent project context, developers use skill.md files to define task-scoped workflows. These are highly specialized instructions, like a specific code review checklist, loaded only on demand. The most common architectural error is attempting to solve every new capability gap by writing another Markdown skill file. This unbounded accumulation of text creates a vulnerability known as context debt. Writing 50 different skill files inevitably creates overlapping semantic triggers. If 10 files contain data processing, mentioning data forces the agent to load all of them. This is the grep tax. The model expends massive computational effort simply searching and parsing competing text files. This actively degrades core reasoning capacity. Latency spikes, and the model loses the token budget required to actually process the codebase. To mitigate this, developers use progressive disclosure. Instead of loading full rule sets, the agent loads a highly compressed manifest that points to bundled logic files only when explicitly invoked by a strict trigger. Advanced context engineering requires an active lifecycle. Developers must rigorously merge overlapping files and aggressively delete redundant skills from the repository. History, rules, and workflows only provide value if they mechanically reduce the cognitive cost of the next task. If they do not, they act as a fatal computational tax on the system. We establish the mechanical boundary by separating instruction from packaging. A skill is a text format that shapes the model's approach. A plugin is simply a distribution manifest that bundles those instructions. Neither of these can execute code. To bridge the gap to physical execution, we introduce the third component, the MCP tool. A true tool requires an executable motor. This is a discrete, compiled binary, a Python CLI script, or an active API endpoint that physically performs the computation, validates the constraints, and mutates external state. The Model Context Protocol, or MCP, establishes the communication layer between the model and the motor. It provides a standardized JSON RPC boundary that isolates semantic generation from the mechanical script. This enforces schema-first design. To trigger an action, the model outputs a strict JSON payload. Arguments and constraints are rigidly verified. If malformed, the action is rejected before reaching the motor. If a tool lacks this mechanical motor, the LLM is left operating in a sensory deprivation chamber. It executes a prompt, receives no physical feedback, and is forced to independently guess whether the external state actually changed. A true motor catches programmatic exceptions. It validates parameters and returns structured, deterministic diagnostics back to the model. This feedback loop allows the agent to recognize an error and correct its approach. True plugins expose mechanical capabilities alongside rigid failure states. By strictly defining what the tool cannot do, the architecture forces the model to act as an orchestrator, completely separating intent from execution. As agents expand into enterprise databases, the ultimate security imperative becomes clear. Cryptographic secrets and authentication credentials must never become model knowledge. If raw API tokens enter the LLM's context window, they become highly vulnerable to prompt leakage and direct exfiltration by malicious third-party instructions. This necessitates the authentication guard. Built on MCP OAuth 2.1, this perimeter isolates sensitive credentials entirely from text generation. The client uses proof key for code exchange, or PKCE, ensuring the token is dynamically fetched and securely held, invisible to the LLM. Furthermore, RFC 8707 resource indicators bind access tokens strictly to the target MCP server, preventing stolen tokens from being replayed. The division of labor is absolute. The model evaluates the user prompt and decides exactly when to invoke an authorized capability. The mechanical guard layer autonomously handles the user consent, the scoping, and the secure transmission of the token. True agency requires a non-human identity gatekeeper. The agent shifts from dangerously borrowing a human developer session to holding its own highly restricted identity. The mature agent architecture is defined by these four specialized layers. Semantic files provide project context, plugins establish identity and packaging, executable motors perform the deterministic work, and auth guards maintain perimeter security. Contrast this highly structured stack with the fragile ecosystem of fake tools, where massive markdown files ask language weights to hallucinate network requests and guess at database schemas. Stop building prompt wrappers to simulate action. Writing operational language into a text file does not computationally automate a process. Before you author 10 broad instruction files, build one localized, verifiable mechanical motor. Write a script that performs a single action, validate its inputs against a JSON schema, and ensure it fails safely. In production-grade enterprise systems, language generation does not run the infrastructure. Deterministic code runs the systems. The agent's intelligence comes from knowing exactly when to trigger those mechanics, how to interpret the diagnostics, and how to recover from failure. Language models are not execution engines. They are the semantic orchestrators of secure mechanical tools.